All right, guys, this set of notes is about exponential regression. Exponential regression is just finding the exponential equation that best fits data. So first we are going to represent some data on scatter plots. Then we are going to describe some associations and estimate curves of best fits. Okay, so here we have an array of scatter plots, and we're going to draw an estimated curve of best fit and then describe each association. I'm going to start on the left. You can see that this looks like the exponential decay graphs that we did in Unit 7. I can actually draw an exponential curve that goes through these points. If my data points fall on my curve of best fit, I say that it's a perfect association. They have to all be on the curve to be perfect. Okay, so this is obviously decaying. So when we're describing that association, we say that that is a negative association. So this is perfect and negative. Okay, the next one is also negative, but it's not perfect. You see how the points get a little fluffy? We can still see the shape of the best fit curve, but it's not perfect anymore. This is strong. Strong and negative. All right, on the third one, we can still tell that it's negative, but the points are even fluffier. They're farther away from my curve of best fit. This is a weaker negative correlation. On the very middle, we can't really tell what's going on. It's not going up, it's not going down, it's kind of just, this has no correlation whatsoever. All right, starting on the right, we have our first positive correlation, but the points are kind of far from the curve of best fit, so we would call this weak and positive. Okay, then we have a strong positive. And finally, perfect positive. Okay, just a reminder, if I say that it's perfect, that means that my data points are actually on the curve of best fit. Oops. Okay, otherwise, if it's not a perfect fit, we just have to say that it's strong. All right, next. So when we look at these, we can see that this one right here, there is some distance between, oops, I didn't mean to do that, some distance between the data points and the curve of best fit. When we make our curve of best fit, we try to minimize that distance. And the fancy name for that is minimizing residuals. Residuals are like the leftover distance between our curve and our data. So if I tried to make a curve of best fit like this for that data set, that would maximize the distance between my data points and my curve. So that would not be a good fit. I want the smallest distance possible between the data points and the curve. That ensures me the best fit. So to minimize the residuals, that just gives us the best fit for our data. Okay, let's do an example on the calculator. Okay, Archie has this table here where he's recorded the maximum height of a bouncing ball for its first 4 bounces. bounce 0 is when Archie lets go of the ball. So that's the starting height or position of the ball. So we are going to make a scatter plot by hand. We're going to label it, and then we're going to do this other stuff. All right. The height of the bounce depends on the bounce number, so I can tell that the bounce number has to be my independent variable and goes on my x-axis. So I'm going to put bounce number down here. Okay, the dependent variable will be the maximum bounce height. Okay, and that is in feet. Looks like I've got 20 ticks, so I'm going to count by twos. Well, I'm counting by ones, but I'm only labeling twos is what I mean. Okay, finally I need a title. Okay, so I just picked max bounce height versus bounce number, and I'm going to plot my data points. I've got starting height of 20, first bounce, max height is 15, then 12, then 9, and 7. Okay, so the next part asks us to use the calculator to find the exponential relationship that minimizes residuals. This exponential relationship that minimizes residuals is just a fancy way of saying curve of best fit. And our calculator can do that for us. So here we go. Before you do anything on your calculator, you're going to want to reset your memory. You're going to hit second, plus, and then 712 to get rid of any weird settings that the kids before you might have used. So second, plus, 712, and that'll reset your memory. Then go to the stat button. First, we're going to edit some lists. So we're going to pick number 1 to edit. And I want you to imagine like list 1 and list 2 is a T-chart of X and Y values. That's what we're going to put in here. So in list 1, we're going to put the bounce numbers. 0, enter, 1, enter, 2, enter, 3, enter, 4, enter. So those are my X's. And then arrow right over to list 2 and put in the bounce heights. 20, 15, 12, 9, and 7. Okay, now these are stored in the calculator for it to use until you delete them. So they're just in there. You don't have to save or anything. So we're going to go back to stat, the stat button. We're done editing, so we're going to go to the calculate menu next. Arrow right to the calculate menu. And then we're going to look through this menu for the exponential regression option. So I'm just going to go down, down, until I see something that looks like exponential regression. And you should see 0 right here. EXPREG, that's the one we want. So if you can remember it's 0, then you don't have to scroll through the whole menu. You can just hit 0. Okay, hit enter a bunch of times until it calculates for you. And here we have our curve of best fit. It's giving us an A value and a base. If you remember from Unit 7, if we don't have a D or a shift, the A value gives us the y-intercept, the starting value, and the base, the B, is what we multiply by, the common ratio. So looking at this, I can write an equation, y equals, with the a value, I'm going to pick this 19.855, which is about 20, right? That we know that that's the starting height. And then in my parentheses, I'm going to put my base, which is 0.770, and raise that to the x power. And that is my exponential equation. Because my base is smaller than 1, I can tell that this is decay. And that gives me that decreasing trend in my graph. All right, now we're going to write that on the line. Okay, so it was y equals 19.855 times 0.770 to the x power. And I did 3 decimal places because it says round to the nearest thousand. So that's 3 places after the decimal because it goes tenths, hundredths, thousandths. Okay, next one says that we have to draw the curve of best fit. Now, this is tricky because I know that the ball actually started at 0.20, but that's not what my curve of best fit equation says. I have to actually use this a value to draw on here. So I'm going to go right underneath 20 and kind of follow the shape of my data. Okay, it's okay if you don't hit the data points exactly. It shouldn't really because this isn't perfect. But it is strong. So when we describe this association, we're going to say that it is strong negative. Okay, we have to state and explain the y-intercept. And it says from the exponential model. The exponential model is your equation of best fit. It's not the data. So when you're explaining and stating your y-intercept, you want to make sure that you're using the 19.855 one. So it's 0, 19.855. It doesn't matter that we know it started at 20. We're explaining the y-intercept from the model. Okay. So basically what this means in context is the height of bounce 0 would be 19.855 feet. We know it's not actually 19.885 feet, but that's what it would be according to the model, so we have to say that. According to the model. Now in this unit, we're going to get some really weird predictions according to our models. So if you want to add that the prediction doesn't make sense, that's fine. You can do that if it's appropriate. Okay, last thing we're going to do for this page is use our equation to predict the maximum height of the 6th bounce. Now the bounces are the x's. Okay, so if it's the 6th bounce, that means that my x has to be 6. So I'm going to plug that into my equation like this. Y equals 19.855 times 0.770 to the 6th power. That's what I plugged in right there. So on my calculator, I can do 19.855 times 0.770 in parentheses, power caret 6. And I'm getting 4.138. .138 feet is the predicted height of bounce 6. All right, next page. Okay, here we have some data from the state of Alabama. It recorded its mobile broadband traffic in terabytes from 2006 to 2009. We're going to make a scatter plot by hand and label it. So let's do the scatter plot. Okay, so this is going to be 2006, 2007, 2008, and 2009. This is the year. Oops. And then this is broadband traffic in terabytes. Okay, so this is broad. Traffic versus the year. Okay. We've got to get all the way up to 18.5. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. I'm going to count by twos. So we're going to say that this is 2, 4, 6, 8, 10, 12, 14, 16, 18, and 20. Okay, let's plot the points. 2006, that would be 2.1. Next year, 3.7, so a little under 4. Estimate as best as you can. 2008, a little bit over 8. Gross looking point. And then 2009, 18.5. So 19 would be here, so about a quarter of the way up to 20. Okay, so we're going to use our calculator to find the exponential relationship to minimize residuals. That's going to be our curve of best fit again. Now, when we put these in the calculator, we're going to do a little trick. Do you see how I have 2006 here in the 0 position for the x? I'm going to treat, here, maybe you can't see because I put this thing in the way. I'm going to put 2006 in as year 0. 2007 is going to be year 1. 2008 is going to be 2. And 2009 is going to be 3. And that will give us a much better graph if we use these pink numbers instead of the actual year. So again, this is going to be 0, 1, 2, and 3. All right, let's put them in the calculator. So we're going back to our stat button, and we're going to edit our lists. Now, before I didn't have any data in there, and now I do. So I'm going to have to clear my lists. So go to list 1, go up to list 1, put your cursor all the way at the top, hit clear, enter, and that will clear list 1 for you. Then you don't have to delete the entries individually. So for list 1, it's going to be 0, 1, 2, and 3. That's our trick for the years. I'm going to go over to list 2. Oops. Clear list 2, so clear and enter at the very top. And it's 2.1 terabytes, 3.7, 8.1, and 18.5. You want to make sure after you do every set of lists that they are the same length. and that you haven't mismatched the points. Like if you get any of these points like flip-flopped, it will mess up your equation because it will think that x's and y's are something else. Okay, back to stat. Now we go to the calculate menu to the right. We're going to go to exponential regression. So all the way down until you see exponential regression, which is 0. Enter, enter, enter until it calculates for you. We have our new equation. I'm going to write it on here like I did last time. So it's y equals our a value. We have to round to the nearest thousand. So I'm not going to use any of this bit. However, this 9 tells me that I need to make that 0 a 1. I have to round up to 951 and get rid of the rest of this. So our a value is 1.951 and our b is 2.077 to the x. So what this is telling us is that we start at about 2 terabytes and then we're about doubling it every year after that. So it's almost like y equals 2 times 2 to the x. It's kind of like that. Okay. 1 point. I might have to flip back to this because I won't remember what it is. I have no short-term memory. Okay. So it's y equals 1 point, already forgot. Is it 951? Times 2.077 to the x. Okay, now we're going to draw it. So make sure that when you draw it, your y-intercept matches your a value. So my a value is predicted to be a little bit under 2, and then it's going to about double every time. Oops. So it's not going to hit all of your points, so it can't be perfect, but it is strong. This would be a strong positive. Okay, from the exponential model, the y-intercept would be the point 0, 1.951. So year 0 is actually 2006, right? 2006. So the model predicts that the broadband traffic was 1.951 terabytes in 2006. That's it. Okay, now we're going to use our equation to predict the mobile broadband traffic for Alabama in 2016. Okay, so this is a little tricky. We're going to have to put on our thinking caps for this. So if 2006 was 0 and 2007 was 1, yada, 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 yada. 3 was 2009. If we continue that pattern, I'm going to use my fingers just to show you how I'm doing this. 2007 was 1, 2008 was 2, 9 was 3, 10 is 4, 11, 12, 13, 14, 15, 16, that should be 10. So our x is going to be 10. So that'll be y equals 1.951 times 2.077 to the 10th power. And we can just put that in the calculator. Okay, so I'm getting, I have to write this down. $2,914.890 terabytes. Okay. Okay. Okay, so traffic will be 2,914.890 terabytes in 2016. Oh, according to the model. Okay, that's not so bad. We can do that. This last one is easy. You'll like this. So the very last thing we're going to do is look at these equations and match them to the scatter plot that they describe. So we have a couple of things that we know from the equations. By looking at the b value here, I can tell that this 2.01, that's growth. And looking at the 0.48, I can tell that that is decay. Also, by looking at the a values, I can tell what the y-intercepts are. So, if I draw a curve of best fit for this data, an estimate, I can see that I'm hitting the y-axis at about 1500-ish, and I have decay. So I can see that that is a match for C right there. So this one is C. Okay, next. On this one, I'm hitting the y-axis in between 0 and 50, maybe at about 25. So that looks like a match for D. For the third one, I have another decay, and it's hitting the y-axis in between 250 and 300. So that looks like a match for 280. This is probably B. Last but not least, I have another growth, and it looks like maybe about 150 for the y-intercept. That looks like a match for A. That's it.